So let's talk about acid strength. So we know that acid-base strength is dictated by whether something will fully disassociate in water or not, but there's factors that will affect that. We have two factors, and these both affect the ease of removing a hydrogen ion from an acid. The first one is polarity. So our first factor of the two is bond polarity. This is your difference in electronegativity between the atoms in the bond. So if you remember, if I have a large difference in electronegativity, I have a polar covalent bond. So if you remember back to 150, where we had our table, and you could actually look up electronegativity values in that table, and then you would compare the two atoms that were involved in that bond and look at the difference in electronegativity. So the larger the difference in electronegativity, the more polar the bond. And what that means is that there's an uneven distribution of electron density in that bond. So one atom is pulling the shared electrons closer to its nucleus. I have a difference in electronegativity. So polarity is also going to affect acid strength, because if I have a really polar bond, then I'm pulling electron density away from that hydrogen, and it might be easier to remove that hydrogen. So if we look at HCl, HCl is a strong acid. It's going to have a dipole moment pointed toward the chlorine. So this is going to have a partial positive charge on the hydrogen and a partial negative charge on the chlorine. And the molecule is polar with more electron density on the chlorine. So the more the polar bond, the stronger the acid. The less the polar bond, the weaker the acid. And if I have a non-polar bond completely, then I don't have an acid at all. So here's some rule of thumbs. And there's more factors that go into play here than just this. So there's two things that we're going to look at, and then we're going to look at the combination of all of them. So the first one is polarity. In general, the more polar the bond, the stronger the acid, meaning that it's going to be easier to disassociate that, because when this disassociates into hydrogen ions, it's going to be full on that electrons, these two electrons that were here that are being shared, one is coming from chlorine, one is coming from hydrogen. Chlorine has basically snatched both of those electrons, and now it's formed an ion. So the more polar the bond, the stronger the acid. The less polar the bond, the weaker the acid. And if I have a non-polar bond, I don't have an acid. Meaning that if I had H2, even though there's hydrogen there, H2 is not an acid. So H2 is a nonpolar bond where I'm going to have equal sharing of these two electrons between my two hydrogens. And this is just hydrogen as a diatomic, not an acid. It has a difference in electronegativity equal to 0. Okay, so that's one factor, is this bond polarity. Our second factor is bond strength. So the stronger the bond, the weaker the acid. The weaker the bond, the stronger the acid. Because you have to break this bond. You have to break this bond in order for this to disassociate. So the stronger the bond, the weaker your acid is going to be. So sometimes you can have a really high difference in electronegativity, but also have a very strong bond, and that's going to keep that from being a strong acid. So HF is a prime example of this. So HF is a polar bond because fluorine is your most electronegative element. So fluorine is much more electronegative than chlorine. So this is going to be a partial negative, partial positive, but fluorine is so small. Fluorine is a very small molecule, and so the nucleus here is really close to this hydrogen. This has a strong bond, which is going to make it a weak acid, even though it's a very polar bond. So you can't just look at one thing, you have to kind of look at it as an overall system. So if we look at this slide here, what you see is that as I increase my bond energy. So hydrobromic acid is down here, hydrochloric acid, and hydrofluoric acid. The bond energy or the bond strength is going to increase as I go up. And that's because my anion here is getting smaller. So bromine is much larger than chlorine. Chlorine is much larger than fluorine. So the smaller this anion is, the stronger this bond is. And so even though this bond is the most polar bond out of all three of these, because it's the strongest bond, then it's going to have a very weak acid strength. So hydrofluoric acid is a very weak acid. Hydrochloric acid is a really strong acid. Hydrobromic acid is a really strong acid. And so you kind of have to take both of these into play. And so that kind of is illustrated in this slide here, where I have decreasing bond strength as I go down a column on a periodic table, and it's decreasing bond strength because those anion component of that is getting larger and larger and larger. So oxygen, sulfur is larger than oxygen, selenium is larger than sulfur. So as I go down the periodic table, my atomic size is getting larger and larger, my bond strength is decreasing, my acidity is increasing. So it's going to be easier to remove that hydrogen. As I go across the periodic table, I'm increasing my electronegativity, which means I'm also increasing my acid strength. So if I look at H2S and HCl, sulfur and chlorine here are going to be very similar in size. Chlorine might be actually a little bit smaller, but because the electronegativity between chlorine and sulfur is much larger, hydrochloric acid is going to be a strong acid. H2S, hydrosulfuric acid, is going to be a much weaker acid. And so you got to look at these combined effects. The difference in electronegativity as well as the bond strength of the atoms that are involved in that bond. So what about oxoacids? So remember, an oxoacid is something where I have a polyatomic ion. So I have oxygen in that acid. And when we looked at the structures of those acids, what we saw is that the acidic hydrogen is always the hydrogen that's attached to the oxygen. So in an oxoacid, the acidic, meaning the hydrogen that's going to be donated, the acidic hydrogen is always attached to an oxygen. So these should be very similar, right? So if I'm just looking at the bond between hydrogen and what it's attached to in an oxoacid, they're all the same. But oxoacids have varying difference of acid strength. So there must be something going on. They all have this structure here. And then that oxygen is bound to something else. So it is going to be bound to some other atom. The strength then is going to depend on this other atom that's bound to oxygen. So it's kind of one removed because this is the bond that we're looking at. This is the bond that has to get broken for hydrogen, for this hydrogen to ionize. I'm looking at one removed in an oxoacid. And some oxoacids are like H2SO4, sulfuric acid, H3PO4, phosphoric acid, HClO, hypochlorous acid. I could have HClO2, chlorous acid, HClO3, chloric acid, or HClO4, perchloric acid. So I could have that series. These are all, even though it's written this way, what this means really is if I look at these, just the series here, this is the polyatomic ion, and the polyatomic ions are going to be written this way. But really the structure of this is hydrogen bound to oxygen bound to chlorine. So in these, even though oxygen isn't written directly beside hydrogen, this is the structure. This is the bond that I'm breaking. This is my atom Y here. HClO2, now I have hydrogen bound to oxygen still, bound to chlorine, which is also bound to another oxygen. HClO3, hydrogen bound to oxygen, bound to chlorine, which is bound to another oxygen, and a third oxygen. And HClO4 would look like this. Hydrogen bound to oxygen, bound to chlorine, which also has three other oxygens bound to it. And so you're looking in an oxoacid, you're always looking at the hydrogen that's attached to an oxygen. We're going to consider what is this other atom that's one removed. So in this case it's chlorine, in this case it's going to be phosphorus, in this case it's going to be sulfur. So factors that influence this is going to be the electronegativity, just like before, the electronegativity of atom Y, so this guy. How electronegative is it? Because that's going to make, the more electronegative Y is, then that's going to shift that YO. And if Y is more electronegative, what it's going to do is it's going to pull electron density away from the oxygen. That oxygen is connected to a hydrogen, so that oxygen in turn is going to pull electron density away from the hydrogen even stronger. So electronegativity is kind of a domino effect here, where if this is more electronegative, then it's going to shift electron density from the oxygen, which is then going to make, so this would be step 1, this happens, then step 2, oxygen pulls even more electron density from hydrogen, which weakens this bond. So 3, this bond becomes even more weak than what you would expect. And so it's a domino effect. It's not this specifically, it's this reacting on this, which reacts on this, which makes this easier to break. So remember, the easier it is to break this bond, the stronger this acid is going to be. So one of those would be the electronegativity of atom Y, and then the other one is the number of oxygens on Y. So as the number of oxygens increases, it's going to change the nature of this bond. So if we look back here, if I want to apply this here, so my difference in electronegativity is going to be the same for all of these because chlorine is the same for all of them. But my acid strength is going to be very different among these 4 here. This is going to be my stronger acid. So the more oxygen atoms on Y, the stronger the acid. These 3 here are all weak acids. This is my strong acid here, my perchloric acid. These appear, all 3 of these are going to be weak acids. So there's a couple of factors for an oxoacid is you're going to look at the electronegativity of atom Y. So that's the one removed from the oxygen here. So it's one bond removed from the bond that you're looking at. The more electronegative this is, the stronger the acid is going to be. The more oxygens that are on Y, the stronger the acid's going to be. Let's consider H2SO3 versus H2SO4. Which one is going to be the stronger acid? Well, S is the same for both, so my difference in electronegativity on atom Y is going to be the same, but this has 4 oxygens and this has 3, so this is going to be the stronger acid of those 2. If I look at HNO3 versus HNO2, nitrogen is the same, so my difference in electronegativity is going to be the same, but this has 3 oxygens, this has 2, so this is going to be my stronger acid here. If I go back up to this difference in electronegativity, if I look at HOCl, so this is hypochlorous acid, this is hypobromous acid, and hypoiodous acid. And so now I have only 1 oxygen attached, so they're all comparable by that standard, but I have different Y. This is my atom Y. My electronegativity is going to go up. So bromine is going to be more electronegative than iodine, and chlorine is going to be more electronegative than bromine, which is going to make this acid stronger than this one and this one. So in terms of acid strength, because they're all the same in terms of the number of oxygens bound, this is going to be the stronger of the 2. This will be a little bit weaker, and this will be the weakest. These are all weak acids, but of these, this is going to be the stronger of those weak acids, meaning that it's going to be able to disassociate a little bit more. All right, so one other thing I wanted to cover, and I'm going to do some generic ways that we could write an acid and a base, and we're going to do this a lot. So if I just have HA, this is my generic formula for an acid. Here's my ionizing hydrogen and the anion that's with it. So HA, if I draw the single arrow here, this is my anion that's disassociated here. This is my hydrogen. If I have my single arrow, then this indicates that this is a strong acid, and I have complete disassociation, or we could call that complete ionization, meaning that I've taken this and I've formed ions. So this would be complete ionization. So we'll call it both things. So those mean the same thing. It disassociates into ions. So this single arrow here denotes that it's a strong. If I have my generic acid here, and now I have my double arrow, and I have the same products. So the only difference between these is now I have this double arrow. This means I have a weak acid, and I have partial dissociation, or I could call that partial ionization. So it only partially ionizes. Partially disassociates, partially ionizes. And I could do the same thing for a base. My base is going to look a little different. So base, I'm going to have water in my equation. Here, water is just understood because these are aqueous solutions. So I could do the same thing for base, and I could have generic base B in water goes to BH plus OH minus. Right, so this is my definition of a base, is that it's produced hydroxide ion in water, however it did it, whether it pulled a hydrogen ion off of this. This single arrow here, this denotes that I have a strong base, because I have complete dissociation, or you guessed it, ionization. Now I can have a weak base, and it looks the same, but my only difference is I have that double arrow. And so now I have BH plus OH minus, and this is going to be my weak base. And this is partial dissociation or ionization. We can also call these electrolytes. So anything that forms an ion in water is an electrolyte. So acids are electrolytes, bases are electrolytes. This is a strong acid. I could also call this a strong electrolyte, and this would be a weak electrolyte. Same here, strong electrolyte, which means that this is going to conduct electricity really well. So strong acids and strong bases, when you dissolve them in water, you got to be careful because they will conduct electricity very well. Weak acids and weak bases, not so much, because there's less ions in solution. So you need these ions in solution to carry the electrons through the solution. All right, since we can write this as an equilibrium scenario, I can write my law of mass action. So you knew this was coming. My law of mass action. So we'll take acid strength, and Ka. And K, remember, this is my equilibrium constant. And now my A denotes that I'm looking at acid dissociation. That's what little a means. So if I go back to my generic partial ionization here, my law of mass action, I could write a law of mass action for this. So my Ka for this would be the concentration of my anion component, the concentration of my hydrogen ion component over the concentration of my undissociated acid. And so the bigger Ka is, then the more that this is disassociating. The smaller the K is, the lower amount of this is going to disassociate, and I'll have mostly undisassociated, unreacted acid here. And I can do the same thing with Kb. So Kb, I could look at this and write a Kb for it. So let's do that real quick. So Kb now, this means my base dissociation. Now there's something important here in that this is liquid water. So remember, in a heterogeneous scenario, this is not going to be in your law of mass action. So I can ignore the water here. So when I write my Kb is just going to be the concentration of BH plus and OH minus over the concentration of B. And this just falls out of that law of mass action. All right, the last thing that I want to leave you with in this part is my 6 strong acids. So if you're like, wow, this is really complicated, now do I have to memorize a whole bunch of stuff? You don't, but what I would like for you to take away are the 6 strong acids. It's good to put these into your memory bank because every acid that isn't one of these 6 is automatically a weak acid. So if you learn the 6 strong ones, then you automatically know the weak ones because they're everything else. So I have these 3 binary acids, hydrochloric, hydrobromic, and hydroiodic are strong acids. H2SO4 is a strong acid. HNO3 is a strong acid. And HClO4 is a strong acid. So I have 3 binary and 3 oxoacids, and these are your 6 strong acids. So I'm going to leave you with that little nugget, and we will come back for part 2.